First of all, let us discuss what we have discussed so far. F of d into y is equal to r of x. What is this equation? This equation is nth order linear ordinary differential equation with constant coefficients, and our goal is to solve or to find the solutions of this differential equation. So to find the solution, we divide this equation into two parts. First, we find complementary solution. In the last session, we already discussed how do we find the complementary solution. So let us share 1 minute with the complementary solution as the revision. For the complementary solution, we consider right hand side 0. Then we have f of d into y equal to 0. We are interested in non-zero solutions, so y must be non-zero. Therefore, f of d equal to 0. This is known as an auxiliary equation. When f of d equal to 0, we have the different values of d. So suppose this is the case that d has two real roots which are unequal. Then how do we write the complementary solution? c1 e raised to m1x plus c2 e raised to m2x. We are mostly interested in these two functions, e raised to m1x and e raised to m2x. Suppose m1 is equal to m2, then the solution is c1 e raised to m1x plus c2 x e raised to m1x. If I don't write x here, then the functions are e raised to m1x and e raised to m1x. The functions are same. They are linearly dependent. We are interested in linearly independent functions. That's why we multiply by x in the case when the roots are equal. When the roots are complex, alpha plus I beta, then we have real part alpha and imaginary part beta. Real part alpha becomes the power of exponential e raised to alpha x, and beta will be appeared in the trigonometric functions cos beta x and sin beta x, and then we design the linear combination e raised to alpha x into c1 cos beta x plus c2 sin beta x. As you know that the constants c1 and c2 are real constants. The other part is today's goal, particular integral. This you may also say that this is the particular solution of this differential equation. Now we find the other part of the solution, that is known as particular integral, where y is considered as, or we make the subject y. This is equal to 1 upon f of d into rx. Okay, so now let us look at this rx. This is the function of variable x. So we have different choice over the function. Our first choice is, suppose rx is exponential function. Suppose rx is trigonometric function, either it is cos x or sin x. Suppose rx is the polynomial function x raised to n. Right? You may recall the Laplace transform session also, where we found the Laplace transformation of important functions: exponential function, trigonometric functions, cos x, sin x, cos hyperbolic x, sin hyperbolic x, and t raised to n, the polynomials, right? Likewise, here we have the important functions. Our first concentration will be on exponential, then trigonometric, and then polynomial. Then we make the combination. So here I make the combination of blue color with green color. Blue color is on the top, so our first priority is on exponential, multiply by x raised to n. So whenever we have this situation, first we deal with exponential. So that's why I put the blue color on the top and green color in the bottom. The next combination is blue color with red color. So exponential with trigonometric function e raised to x into cos bx. Please make sure here we have another constant b, right? So otherwise, what happen if I write here? Then this is the fixed constant, but we have two different constant. One is for exponential, another one is for trigonometric. Or we have the combination e raised to x into sin bx. One more combination you can design, which is red color with green color, cos x into x raised to n or sin x into x raised to n. But we are not going to discuss because we deal with this case, right? This is actually included in these two cases. So now let us consider how do we find the particular integral with the particular example. The first example is d2y by dx square minus 3dy by dx minus 10y is equal to e raised to 3x. Our goal is to find the solution of this differential equation. That means we have to find two parts. One is complementary solution and another one is particular integral. So let us discuss the complementary solution. We represent this function in terms of d. This is the second derivative. So we have d2y minus 3 dy and minus 10y is equal to e raised to 3x. Now for complementary solution, what we do? We consider the right hand side equal to 0. So we have the equation d square y minus 3 dy minus 10y equal to 0. We take y common. So we have d square minus 3d minus 10 into y equal to 0. And you know very well that we are interested in non-zero solution. So we must have d square minus 3d minus 10 equal to 0. We factorize this thing. Yes, this is known as auxiliary equation. Now no need to repeat the thing every time. The factorization of this is d minus 5 into d plus 2 equal to 0. So we have two roots, minus 2 and 5. These two are real roots. These two are unequal. So how do we design the solution? The case 1 of complementary solution. ycx is equal to e raised to minus 2x. See, this minus 2 appears in the power of exponential function. Likewise, this 5 will be the power of the another exponential function e raised to 5x. These two are different functions. We multiply first function by c1, another function by c2, and then addition. So the complementary solution is this: ycx is equal to c1 e raised to minus 2x plus c2 e raised to 5x, where c1 and c2 are real constants. Now let us go for the particular integral. So for the particular integral, let us assume that this is the solution of the given equation. We have given this equation: y double dash minus 3y dash minus 10y is equal to e raised to 3x. This assumption is important. How do we assume this? C into e raised to 3x. Why I assume only this thing? Our assumption will be on the base of right hand side. Right hand side has exponential function. That's why I'm assuming the same exponential function with some constant into e raised to 3x. This is the very much important thing. Now as we are saying that this yp is the solution of this differential equation, what does it mean? When I substitute yp in place of this y dash, that means derivative of this, we substitute here. Again we differentiate, so the second derivative of this we substitute here. It satisfies this equation. But here the constant c is arbitrary constant. So let us find the first derivative of this, which is, what is the derivative of e raised to x? That is a into e raised to x. So this is 3c raised to 3x. The second derivative is this 3. Again 3 we have, so this is 3 into 3 is 9c e raised to 3x. Now we are going to substitute y double dash, y dash and y in this equation. This is the equation 1, which is the given equation. So what we have? Y double dash 9c raised to minus 3x minus 3 into y dash is 3c raised to 3x minus 10 y c into e raised to 3x equal to the right hand side e raised to 3x. Now look at the left hand side. This is 9 minus 9. So this will be cancelled out. Minus 10 c raised to 3x equal to this. First two terms will be cancelled out. 9 minus 9. So this is minus 10 c raised to 3x is equal to e raised to 3x. E raised to 3x we can cancel out from both the side. So we have minus 10c is equal to 1. So we have value of c. This is minus 1 upon 10. So let us substitute c is equal to minus 1 upon 10 into the assumption. So the particular integral ypx is equal to minus 1 upon 10 e raised to 3x. So to find the particular integral is not the difficult thing. We have complementary solution. We already found this is the particular integral. So now we are able to write the general solution. General solution is yx is equal to ycx plus ypx. What is ycx? This is c1 e raised to minus 2x plus c2 e raised to 5x and plus ypx. Now let me concentrate on the solution. Look at here. The solution has two constants, c1 and c2. This is the second order differential equation and the solution of second order differential equation contains always two constant, right? Yp, this is particular integral. Keep in mind, particular integral never contain arbitrary constant. Here we have the fixed constant minus 1 upon 10 and the given function e raised to 3x. So this is the general solution where C1 and C2 are real constants. Now look at here, ypx is equal to minus 1 upon 10 e raised to 3x. We are going to find the same particular integral by another method. We represent the function yp is equal to 1 upon f of d into e raised to 3x. What is f of d? D square minus 3d minus 10, that you know. So this is 1 upon d square minus 3d minus 10 e raised to 3x. Now what we do? We substitute these 3 is blinking, you know, it's the power of exponential function. This is actually the right hand side, e raised to 3x. This is the right hand side. So we substitute these 3 in place of d. It becomes this 3 square minus 3 into 3 minus 10 is equal to e raised to 3 square. So this is 9 minus 9 will be cancelled out. This is minus 10. So we have minus 1 upon 10 e raised to 3x. You know, so I think this method is very much easy than this. Here we find first derivative, second derivative and substitute to the equation, and then we compare the coefficient of e raised to 3x, which gives us c is equal to minus 10, 1 upon 10. Whether here we just substitute this 3 in place of d and we have the solution. In the examination you can apply any method, this method or this method, to find the particular integral. Now let us go for the second example. The second example, fourth derivative of y minus y is equal to 3 times e raised to x. Let us represent the given function in terms of d. So this is fourth derivative, which gives us t raised to 4 y minus y is equal to 3 times e raised to x. Actually here we have equal to 3 times e raised to x. The same thing we have. First we go for the complementary solution. So for the complementary solution we consider right hand side 0, that you know very well. We take y common. We are interested in non-zero solution. So d raised to 4 minus 1 is 0. In the last lecture we already discussed this example. We factorize d raised to 4 minus 1. So we have the roots 1, minus 1, I and minus I. Now I am not repeating all such things. Look at here, minus 1 and 1. These two are real and unequal. So we have e raised to x, e raised to minus x. These are the complex. 0 plus 1 into I, 0 minus 1 into I. So e raised to 0x, which is 1. Then we have two functions, cos 1 into x, sin 1 into x, which gives us cos x and sin x. So four functions we have: e raised to x, e raised to minus x, they are coming from the real roots; cos x plus sin x, they are coming from the complex roots. Then we multiply by the constants c1, c2, c3, c4 and take the addition. This is called the linear combination of these four functions. Okay. Please keep in mind, we have four functions: e raised to x, e raised to minus x, cos x and sin x. Now let us go for the particular integral. The same method we have. Ypx is c into e raised to x is the solution of the given differential equation. Here right hand side is 3 into e raised to x. So this e raised to x, which I am assuming in the solution. Let us find y dash, double dash, third derivative and fourth derivative of y. This is exponential function which has derivative itself. So this is first derivative. You can verify the second derivative, third derivative and fourth derivative. All the derivatives are equal. Now let us substitute to the given equation. So what we have? Fourth derivative of y is c into e raised to x minus y minus, this is y, is equal to 3 raised to x. Left hand side, c raised to x minus c raised to x is 0. Right hand side is 3 raised to x. Okay, what does it mean? That means 0 is equal to 3. Is it possible? This is not possible. That means our assumption c into e raised to x is not true. Right, something is missing here. Now let us see what is happening with very easy method. This is also known as the shortcut methods. We have 1 upon f of d, 3 e raised to x. F of d is what? D raised to 4 minus 1. 3 into e raised to x. E raised to x. Right. This can be represented by 1 into x. So in the last method we substituted 3 in place of t. Here we have given 1 in place of 3. So we substitute d equal to 1. When we substitute d equal to 1, this is 1 raised to 4 minus 1. So this is 0. 1 upon 0. 1 upon 0 is infinitive or undefined quantity, you can say. That means both the method fails here, right? Actually, this is the another representation of this method. So what is wrong here in the assumption c into e raised to x? In the last example also we assumed the right hand side with the arbitrary constant, but here the same assumption is not working. That is only because of, look at the complementary solution. Complementary solution has 4 functions: e raised to x, e raised to minus x, cos x and sin x. This e raised to x, c1 into e raised to x. So this e raised to x is the right hand side e raised to x. Right. So the right hand side is the part of complementary solution. Whenever this situation occurs, the same right hand side will not be our assumption. As we know that in the final solution, ycx plus ypx, all the 5 functions must be different. But here the function c raised to x, which is the part of this. That's why this assumption is not working here. So what we do? In the last lecture also this kind of situation occurs. That time we multiplied by x. Right. So here the same thing we apply. We multiply by x. Ypx is equal to cx e raised to x. Now find the first derivative. I differentiate e raised to x, which has derivative e raised to x. Then the derivative of x is 1. So this is c into e raised to x. The second derivative is cx e raised to x plus 2c e raised to x. So second derivative is not difficult. This is very simple derivative concept. So third derivative and fourth derivative. You please verify this thing, that fourth derivative is cx e raised to x plus 4 times c e raised to x. We substitute the derivatives in the given function. Right. So y4, fourth derivative is this minus y. Y is cx e raised to x is equal to 3 e raised to x. These two will be cancelled out. So we have 4c e raised to x equal to 3 e raised to x. So 3 is equal to 3 upon 4. This is very simple calculation. That's why I am not mentioning all the steps in brief. C is equal to 3 upon 4. So what is yp? Yp is 3 upon 4 x e raised to x. Right. I forgot to write x here. This is 3 upon 4x e raised to x. So the general solution is this: yx is equal to ycx plus ypx, c1 e raised to x plus c2 e raised to minus x plus c3 cos x plus c4 sin x plus 3 upon 4 x e raised to x. Now observe these 5 functions: e raised to x, e raised to minus x, cos x, sin x and x e raised to x. All the functions are different. Right. See, if I consider this without x, then 3 upon 4 e raised to x, which becomes the part of this. Right. That's why we multiplied by x. This is the solution. Now let us see how do we handle or how do we find the same thing 3 upon 4x e raised to x using this method. What we do now, when we have the denominator is 0, after substituting d is equal to 1, we differentiate the denominator. Denominator is d raised to 4 minus 1. We differentiate with respect to d. So the derivative is 4d cube. D raised to 4 has derivative 4d cube. 1 has derivative 0 minus 0. So it is 4d cube. When we differentiate then we multiply by x also. In future, the second derivative of the denominator, third derivative of the denominator also we shall discuss, right? That time, how many times we are going to differentiating, that many times we multiply by x. Again I repeat, we differentiate this thing. When do we differentiate? We multiply numerator by x. So 1 into x is x, the quantity 3 into a raised to x. So again e raised to x is 1 into e raised to x, right? So we take d is equal to 1, which becomes x upon 4 into 1 cube 3 raised to x. This is 3 upon 4 into x e raised to x. So the same yp we have 3 upon 4 x e raised to x, 3 upon 4 x e raised to x. So the general solution of this differential equation is c1 e raised to x, c2 e raised to minus x, and the tail. Okay, let us refer these two examples again. The differential equation y double dash minus 3y dash minus 10y is equal to e raised to 3x has this solution. The differential equation fourth derivative of y minus y is equal to 3 e raised to x has this solution. I am interested in the discussion of the solution nature. In this example, our first solution was this complementary solution e raised to minus 2x and e raised to 5x. To find particular integral, we always compare the right hand side with these two functions. Is e raised to 3x is repeated here or not? If not, then assume the constant into e raised to 3x and find the constant. Whether in the second example, ycx is this e raised to x, e raised to minus x, cos x, sin x. The same questions I asked to the example. This e raised to x is repeated with this or not? Yes, here e raised to x is going to be repeated. So what I do, I don't assume only constant into e raised to x. I assume constant into x e raised to x, right? To make the function linearly independent with these functions. So here you can check e raised to minus 2x, e raised to 5x, e raised to 3x are linearly independent functions. Whether here e raised to x, e raised to minus x, cos x, sin x, x e raised to x are linearly independent functions. This is the fourth order differential equation. So we have 4 constant. This is second order differential equation. So we have 2 constant. In the next lecture, we shall discuss when the right hand side is trigonometric functions or polynomial function.